This first mini lecture introduces the components of a chemical reaction equation and the importance of balancing chemical reactions. The first thing to recognize about chemical reactions is that they represent a reorganization of atoms from a set of initial elements or compounds called reactants to form a final set of elements or compounds called products. Images of the reactants and products are provided here to make it easier to see how the atoms have been rearranged. Notice that the black carbon atom in the reactants is bonded to white hydrogen atoms, but in the products, the black carbon atom is now bonded to red oxygen atoms, and the white hydrogen atoms are now bonded to red oxygen atoms as well. When atoms rearrange in a chemical reaction, some bonds are broken and new bonds are formed. However, mass is conserved. So all the atoms present in the reactants must also be present in the products so that the total mass of reactants matches the total mass of the products, as we've seen previously with the law of conservation of mass. The reactants in the reaction below have one carbon atom, 4 oxygen atoms, and 4 hydrogen atoms. The products also have one carbon atom, 4 oxygen atoms, and 4 hydrogen atoms. So this means that the reaction as written is balanced, and looking at the coefficients in the balanced reaction, it requires 2 molecules of oxygen for every 1 molecule of methane, or CH4, to produce 1 molecule of CO2, or carbon dioxide, and 2 molecules of water, or H2O. Finally, note that the type of reaction shown here is called a combustion reaction, and they always involve a hydrocarbon reacting with oxygen to form carbon dioxide and water, as well as other oxide products if there are other nonmetals in the original hydrocarbon. A hydrocarbon is just a molecular compound that contains mostly carbon and hydrogen, but may also contain other nonmetal elements. Remember from a previous mini-lecture in Chapter 2 that the symbols used to indicate atoms and compounds have a very specific notation that includes numbers as either coefficients or subscripts. Subscripts are used in molecules to indicate the number of atoms of a specific element in the molecule and imply bonding between that element and other atoms in the molecule. Coefficients indicate more than one separate atom or molecule depending on what follows the coefficient. Note below that while 2H indicates 2 separate hydrogen atoms, 2H2 represents 2 separate hydrogen molecules, which each contain 2 hydrogen atoms that have a bond between them, and as a whole, these 2 molecules give a total of 4 hydrogen atoms spread over the 2 molecules. In reactions, it is also important to indicate the physical state or phase of the chemical species involved in the reaction, and this is done with state labels, indicated in parentheses with an italicized abbreviation of the state. The 3 most common states of matter, solid, liquid, and gas, have fairly obvious state labels as shown here for solid sulfur, liquid bromine, and gaseous chlorine. The 4th state label, AQ, is used to indicate when an ionic solid or molecular compound is dissolved in water as individual ions or separate molecules, creating an aqueous solution of the substance. Pronounced aqueous or sometimes aqueous, depending upon where you learn it from. Note the purple and green aqueous solutions in the image are comprised mostly of water, but the color of the solutions indicates that there are ions of an ionic compound dissolved in the water. However, not all solutions will be colored, as many ionic compounds are colorless, and therefore solutions of such compounds would be indistinguishable from pure water to our eyes. Solutions will be introduced in another mini-lecture for this chapter. Physical states are critical in certain situations in chemistry, as we will see later on in this chapter. For example, the 2 reactions below may look identical, but note that the water produced in the first reaction is a gas, whereas the water produced in the second reaction is a liquid. This could be due to the reactions taking place at different temperatures, where the first reaction is conducted above the boiling point of water, and therefore water is produced as a gas, whereas the second reaction is conducted at room temperature, and therefore the water is produced as a liquid. Technically, these two reactions are different just due to the difference in the state label for water. And in equilibrium and thermodynamic calculations, there would be different factors to consider depending on the phase of the water. So it is important to know which phases you are considering. These concepts will be covered more in Chem 122, but it's best to start good habits early. So always consider and include state labels for all chemical species in your reactions in order to earn full credit on free response problems. When writing a chemical reaction from a word problem, you need to know which reactants and products are being described, as well as the physical states of those reactants and products. Breaking down a reaction given in words requires strong nomenclature skills, so continue to use your flashcards for polyatomic ions, metal cations, and prefixes to memorize the names and charges of the common ions in ionic compounds and the formatting for covalent compounds. Also remember the Hofbrinkel elements that exist as diatomic molecules in their elemental form, as when a problem states that oxygen gas was reacted or produced, you need to know that those words refer to gaseous molecules of O2 and not single atoms of gaseous oxygen. Once you determine the unbalanced chemical equation for a reaction, then you proceed to balancing that reaction by changing the coefficients only. Note that subscripts are modified only when determining the identities of the reactants and products. Once those identities have been determined, you don't want to change the subscripts, or that will also change the identity of the chemical. So balancing the atoms in the reaction will involve adding or changing coefficients that indicate the number of molecules or single atom elements that are involved in the balanced reaction. For a challenge, pause the lecture and see if you can balance this reaction on your own before I review how I like to approach this process. Ready to review? To balance the combustion reaction for liquid propanol, start by identifying the largest or most complicated molecule in the reaction. In this case, the propanol reactant, or C3H7OH. Next, balance the atoms in the molecule that appear in only one species on both the reactants and product side. In this case, carbon and hydrogen. Since there are 3 carbon atoms on the reactant side, then a coefficient of 3 is placed before the carbon dioxide on the product side to ensure there are 3 carbons on the product side. Since there are 8 hydrogen atoms on the reactant side, then a coefficient of 4 is placed before the water on the product side to ensure there are 8 hydrogen atoms on the product side. Next, we balance any remaining atoms in this reaction, and in this case, that's going to be oxygen. Considering our coefficients that we've already added to the reaction, there are now 10 oxygen atoms on the product side, and oxygen appears in both reactants. Therefore, since there is 1 oxygen atom in the propanol reactant, this means we need 9 more oxygen atoms to be accounted for by the O2 reactant. A coefficient of 4 would provide 8 oxygen atoms, but since 1 more oxygen atom is needed, then 4.5 oxygen molecules are technically needed. This can be represented by a coefficient of 9/2. However, fractions are not allowed in balanced chemical reactions, as we can't physically have just half of an oxygen molecule. We need to have whole number multiples of the molecules involved in the reaction. So, at this point, we want to start over, but this time start with 2 molecules of propanol instead of only 1. Starting with 2 molecules of propanol, the steps are similar, but now there will be different coefficients needed to balance the atoms. To match the 6 carbons atoms on the reactant side, a coefficient of 6 is needed for CO2 on the product side. And to match the 16 hydrogen atoms on the reactant side, a coefficient of 8 is needed for water on the product side. Moving on to oxygens again, now there are 20 oxygen atoms on the product side. Since there are 2 oxygen atoms provided by the 2 molecules of propanol, that leaves 18 oxygen atoms that should come from the O2 molecules, which we can get with a 9 for the coefficient on the O2. Note how when you arrive at a fraction for one of the coefficients, that you can adjust all of the other coefficients that were determined up to that point by simply multiplying by an integer to get whole numbers. In this case, I multiplied by 2. Finally, always do a double check of your balanced reaction to make sure that the number of atoms of each element on both sides matches. Here they do, so a final check is to also make sure your coefficients don't have a common denominator that can be used to simplify them to smaller whole number values. In this case, the final coefficients cannot be simplified by dividing by the same whole number, so the reaction is correctly balanced. When balancing reactions with polyatomic ions that are preserved from reactants to products, then you can focus on simply balancing the polyatomic ions as a whole unit rather than counting individual atoms of each element within the polyatomic ion. This makes it easier to balance a problem like this because both polyatomic ions contain oxygens, which could be difficult to balance on their own if we were counting individual elements on both sides of the reaction. But by focusing on the polyatomic ions as a whole, then adding coefficients to balance the metal cations leads to balancing of the polyatomic ions as well, without the need to focus on oxygen individually. Here we can see that by adding a coefficient of 2 in order to balance the hydrogens and another coefficient of 2 for the sodium phosphate to balance the sodiums, we end up noting that both these coefficients give 2 of these phosphate polyatomic ions on both sides of the reaction. And same thing goes for the sulfite polyatomic ion here. We have 3 of those with each of these. So no need to count up the oxygens, just notice how many of each polyatomic ion you have on both sides. This concludes the first mini lecture for Chapter 8. Please note any questions you may have about this material and how it is utilized to solve problems in the suggested end of chapter exercises and the sapling homework for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our required class meetings, and during that time we will focus more on problem solving for concepts in this chapter.